recording the sessions, so maybe we can start. Hello everyone and welcome to the third day of the European Einstein Toolkit Meeting. So we are in the middle of the week and everything is going very smoothly so far. And I hope everybody is also enjoying the meeting. So our first talk will be a lecture on Introduction to Numerical Methods, and it will be given by Hawke. Ian is a professor at the University of Southampton, and he is an expert on neutron star mergers and computational astrophysics. Ian, you know the rules already, but I'll let you know when you have 5 minutes left before the questions, and you can start whenever you're ready.
Okay, so thank you. Hopefully you can all see my slides. This is going to be a rapid surface level introduction to numerical methods, particularly in the context of the Einstein Toolkit, and I'll touch on some of the aspects that have been seen in a number of other talks. So just as a reminder, what we're trying to do when we're solving a system using numerical methods is to take some given model and find one or more observables to a particular accuracy, the tolerance that we wish to find things using the minimum amount of resources. Okay, and in particular, the Einstein Toolkit is based on design decisions that were made 20 to 30 years ago, where the model is GR or GR-like theories, and the particular observables and accuracies were set by the early LIGO LVK requirements, so finding gravitational wave signals from binary mergers to about 1 radian of phase accuracy, and also the machines under consideration were those available at the time, so using the minimum amount of CPU time. Now, in the present day, pretty much all of those expectations, all of those backgrounds are now changed. We're looking at a much wider class of theories than GR. We're looking at multi-physics for neutron stars for beyond ideal matter theories. We're looking at neutrino observations. We're looking at our process nuclear synthesis, electromagnetic signals. Next generation detectors require much higher accuracy, and the computational landscape has changed considerably to include GPUs. And so all of these aspects have changed. Sorry. However, there is one particular thing to note, which is that when I say minimum resources here, we have to include human time as well as computational time. So one of the reasons that the toolkit has survived and thrived, despite the fact that the design decisions made 20, 30 years ago may no longer be perfect, is that from a human point of view, it is much more efficient to use an imperfect few 100,000 lines of code rather than writing your own few tens of thousands of lines of code that might be better suited to what is currently available, just given the time that it will take to make that work. Okay, so the landscape of numerical methods is always discussed in terms of toy models, and that's because we can reduce most interesting physical problems down to slightly more complicated version of these toy models, and it allows us to discuss broad aspects of the numerical methods in that context. So in particular, the four models that we tend to care about are the wave equation, because with Einstein's field equations, that's essentially what weak gravitational waves look like. And that's the picture we see in the top left of waves propagating at constant finite speed. And then we've got charge conservation coming into electromagnetism, coming into fluid mechanics, that pushes information around again at finite speed. Then we have the nonlinear balance laws that follow automatically from the conservation of stress energy. That typically gives us nonlinear balance laws. So in particular, this flux function is nonlinear, and that leads to the steepening of waves. And the typical toy model is Berger's equation, where this flux function is quadratic in terms of the unknown variable. And finally, we have the exchange of information between, say, space-time and matter, or different aspects of the matter. So this could be the weak coupling through different parts of the stress-energy tensor, or it could be reaction networks or similar things. And that tends to lead to local reaction on some timescale here. Now, all of these aspects lead into different parts of the numerical method. They will constrain our accuracy and our stability in differing ways. And we need to take all of these into account. Okay, so the first thing to discuss is how we actually tend to think about this very complicated system of multiple pieces of weakly coupled physics. And the method that is now standard in the field is to do what's called a semi-discretization. That is, we take our system of partial differential equations, we introduce some discretization in space, for example, just a set of grid points that are separated by, for example, an evenly spaced spacing delta x, that's just a representative length scale. What this does is it allows us to approximate any spatial derivatives in terms of discrete couplings of the solution as represented at the neighboring points. What this does is it converts our PDEs to ordinary differential equations, which we can then, in principle, solve. The solution of the ODEs will also introduce some representative timescale like this. Okay, so the method of lines is very useful because it allows us to deal with the different aspects of the physics as simply as possible by decoupling them at the level of the solvers. So that's the huge advantage. It simplifies the coupling. However, we see a range of disadvantages coming in. One just follows automatically, which is that the aspect of causality will lead to a stability limit. Essentially, if this point at a future time depends just through the causal light cone on, that's the yellow part here, on this yellow region, then the discrete stencil, that is the parts that the numerical method has to take into account, has to include that. And that will restrict the time step and also affect the cost. The more time steps that we have to take, the more we lose accuracy and the worse the efficiency gets. So while the bulk of the issue that we have is about the effective light cone of the problem, which leads into the which comes from the propagation of information, gravitational waves, acoustic waves, and so on and so forth. We also have the local exchange of information through relaxation terms and so on and so forth on the sum timescale. And this also impacts stability purely through the time evolution. So we have two ways of solving the differential equations. We can either solve explicitly by evaluating all of the terms on the right-hand side in terms of known data, or we can solve it implicitly by evaluating all of the terms on the right-hand side in terms of the unknown data. Both of these work. The first term is explicit. The second one requires the solution of a nonlinear system. And we see that when they are both stable, the implicit method here suffers considerably with loss of accuracy, in addition to being considerably more expensive. However, when the exchange of information happens on timescales that is roughly less than the numerical time step that we are using, the explicit methods become unstable and just straight up explode. So the implicit methods are necessary in order to solve when the exchange physics is happening on very short timescales. This is a particular problem for example, neutrinos and radiation transport. I should emphasize that just because implicit methods are stable does not mean they are accurate. Here is an implicit method applied to the van der Pol equation, which is extremely stiff, so the tau here is extremely small, and we see that the results are order 1 incorrect. Right. Inside the toolkit, the method of lines Thorne implements the method of line approach. It does all the time evolution, and it focuses on explicit methods. It is perfectly possible to add implicit methods to MOL, especially through the IMEX methods, which solve as much as possible explicitly and some parts implicitly. As far as I know, that's not currently in the standard distribution of MOL. Okay. For IMEX methods, have a look at the work of the Valencia groups and Isabel Cordero Carrier in particular. So in order to complete our description of the numerical method, we need not just the update in time, but also the way that we calculate the spatial derivatives, the way that we semi-discretize. And in essence, this boils down to how we're representing the continuum fields phi as a function of space in terms of a finite amount of data. And there's three standard approaches. In approach one, we introduce a grid of points, and the values that we're storing are the values of the function at those points. And that allows us to construct finite differences. In approach two, we discretize our spatial slice into individual cells, and we represent the data by the integral average of the field over that cell. And in case three, what we're doing is we're again discretizing the spacetime into cells, but within each cell, we're storing multiple numbers representing the modal coefficients in terms of some basis function. Think about, for example, a truncated Fourier series expansion inside each cell. So all of these are practical. All of these would lead to semi-discretizations. The Einstein toolkit tends to work best with finite difference and finite volume methods because of the design decisions that were made and because of the way it does the communication between different grids. There is one additional approach that was discussed by Stefan Osvog on Monday, and that's smooth particle hydrodynamics, where the field is represented by a set of packets, each of which is called a particle. The advantages that Stefan discussed are perfect conservation of, for example, mass, which makes it easy to track, for example, ejecta from neutron star mergers. But these are incredibly complex, and one of the main sources of complexity is that the interaction between neighboring packets means that you need to have a description of how one packet talks to another one. And you do this essentially by putting a function basis around each packet that makes this a bit like an overlapping set of function bases, but the center of each function basis can move from time to time. Now, the Einstein toolkit can track particles. So, for example, the GR Hydro code allows particles to be advected along with the flow, or particle-like behavior can be done to track the punctures of black holes. But the interaction step through kernels is not available through the toolkit. For that, take a look at Stefan's talk and Sphinx BSSM. The toolkit is just not well suited to this approach. Right, so the approaches that the toolkit is well suited to would be, for example, finite differencing. And this is the very well-studied approach. So the idea is we have a grid of points. We know the field at those points. What we do is we interpolate those points using a simple function, such as a polynomial, that we can easily differentiate. We then approximate the derivative of the function with the derivative of the interpolant, phi hat. And there's a number of tools that interact with the toolkit in order to convert a set of differential equations using this sort of approach, polynomial interpolation, replacing the derivatives with some finite difference approximation. So in particular, crank and NumPy are the two main tools that tend to be used. So the order of the polynomial has an impact on the accuracy of the solution. Here I'm using essentially an advection equation, and we see using a fourth order polynomial gives us much better accuracy than using a second order polynomial, which is hardly a great shot. So in the numerical methods literature, what people do is they tend to quantify the order of accuracy of the method, which is compared to the representative step length of your grid, delta x, how does the error scale? So second order methods scale as delta x squared, fourth order delta x to the 4. And we will often link that to the number of degrees of freedom, which for finite difference methods is the number of points. So you'll see plots like the one in the top right, where the logarithm of the error scales with the logarithm of the points, and the slope gives you the order of accuracy of the method. And we can see that for given error, the number of degrees of freedom needed for the higher order scheme is much, much lower. Therefore, these methods appear to be more efficient. However, higher order methods need more information, and that greater information comes with a cost. So what we should really be doing is comparing the time taken to get to a given error threshold. That's how we properly measure efficiency. This is, of course, not straightforward to do because it depends on the implementation, it depends on the set of equations, and a whole bunch of other things. So the literature tends to use figures like the top right. What we're really interested in is figures like the bottom right. In particular, we can see here, if we wanted the error at, say, 10 to the minus 1, then second order methods would be more efficient. However, for gravitational wave applications, we typically want very low errors, say 10 to the minus 8, and so we see the efficiency of fourth order methods still wins out. Okay, so it's that resource calculation that we have to do, and why we can't just rely on the plain stuff from the literature. Now, for linear finite difference methods, we can in fact get a number of useful analytic results. And we do this by essentially looking at the error introduced in two different ways. So we plug in a single Fourier mode, basically a sine wave, and we split the errors introduced into how does the amplitude behave and how does the phase behave. And this, of course, depends on the frequency of the input wave. Now, this was calculated by Cross and Oliver back in the 70s. And in essence, what you can do is specifically for the phase errors, which is what we really care about for gravitational waves, you can estimate how the grid spacing affects what the phase error is. And then you can plug in, say, okay, I want to do the calculation. I want to compute numerically the phase position of a wave for a given frequency over a given time period up to a given error. And here are the numbers that I plug in for essentially the initial LIGO case. And we see if we'll be using second order methods, we would need 10-meter resolution over the entire grid from the source out to the gravitational wave detector. And that is completely impractical. A typical numerical grid is going to be of the order of hundreds of meters. Even in the strong field zone, we want accuracy all the way out to the wave zone. So we see the rapid improvement with higher order methods is absolutely essential in order to even meet initial design sensitivity. When moving towards 3G detectors, which have a wider sensitivity band and have greater phase error requirements, we see even with the high order schemes, we're going to need to use a very large number of points in order to capture these waves accurately. Okay, so if finite difference methods are going to struggle, or if we have to go to very high order finite difference methods, why don't we just use all of the grid point information available to us and see what that gives us? That's one way of thinking of spectral methods, that it's basically using all of the information on the grid. The alternative way of thinking about it is to use a function basis expansion. Here I've used a Fourier expansion. And the thing that we're interested in modeling is, in fact, the modal coefficients. Then when we take the derivative of this truncated approximation to the function, what we have is a dense matrix multiplying all of the modal coefficients. What we find here is that the error falls off exceptionally quickly. In comparison to the finite difference schemes here, we see the error in approximating the derivative is hitting floating point accuracy already at a few tens of modal coefficients. In particular, we're seeing exponential convergence. This is far faster than we should expect for any finite difference method whatsoever. Now, that's purely the accuracy of the semi-discretization, so purely representing the derivative. We're going to be limited when we go to time evolution in two ways. One is the accuracy of the time evolver. Here, because I was only using fourth order in time, we see this hard limit on the spectral scheme. And the second problem is that the effective time step restriction is not independent of the number of modes. It scales in such a way that we have to take more steps with the more modes that we include. This means that the cost in order to get to a particular solution with time gets worse. However, for smooth data, spectral methods is still massively better than any finite differencing scheme could ever be. Now, the Einstein toolkit does not contain spectral evolution. For this, you want to be looking at the REN or you want to be looking at SPEC, and they are going to have huge advantages. However, there are a few explicit disadvantages that we have to touch on. The first one is, of course, working with discontinuities. And because we've talked about spectral methods in terms of truncated Fourier series approximations, you're probably all well aware of the Gibbs oscillation effect. If you try and fit a function basis to a discontinuous solution such as this, then you get overshoots, you get oscillations near those jumps, and those oscillations do not converge. And that's what we're seeing in the bottom right, where the black curve is the spectral approximation to the derivative, which should essentially just be piecewise constant everywhere. And we see as we increase the number of degrees of freedom, it's just getting steadily worse and worse. The finite difference method does not have these problems except at the jumps where it gives very large specs. So discontinuity is problematic for standard finite differences, catastrophic for spectral methods. So the solution for dealing with discontinuities is to use piecewise polynomial reconstruction, where what we do is we interpolate a data-dependent set of points. You look at the data, see whether or not it is behaving nicely, and if it is jumping, then you offset the points that you feed into the polynomial interpolator. Standard methods for doing this are called the weighted, essentially non-oscillatory methods. So ENO is just saying, look at the polynomials. If they start oscillating, then shift them off to one side. What we see here is in blue, the WeKnow scheme behaving very nicely. And as we increase resolution, it converges. Now, these formally converge only at first order jumps. However, they do retain high order accuracy away from the jumps. The downside is that they are much more expensive, partly because they have to consider multiple different stencils at every single point, but mainly because they are data dependent, which means that it's not possible for the compiler to optimize these in any nice way. Okay, now WeKnow type methods are implemented repeatedly in the toolkit because they're absolutely essential for dealing with nonlinear matter models like Hydro. So you'll see all of the Hydro codes have this type of scheme implemented with it. A second issue that we have to deal with is nonlinearity. So particularly in the evolution of matter, where we have balance laws of this particular form, what we get is the formation of shocks, discontinuities, from smooth data. So at a discontinuity, this derivative just does not make sense. So what we have to do is to basically integrate this over a spatial cell, over a fluid element, in order to get the weak form. So by integrating over the volume, what we do by integrating by parts is get rid of this total derivative and lead us with a surface integral of the flux, which can be implemented in the discrete form like this. So finite volume numerical methods are basically storing this integral average as this phi hat I and computing the intercell fluxes, these FIs here. What we need to do in order to solve for fluids is both use non-oscillatory reconstructions like WeKnow and also find an appropriate way of calculating the flux through cell boundaries here. And this is done in all of the toolkit codes like geometry. Now, it is absolutely essential that you can treat shocks inappropriately. The emphasis here and through much of the literature is on conservation law forms or balance law forms. And the reason for that is that if you start with a non-conservative form like this, so this is Berger's equation, dtq plus q dx q equals 0, then that is equivalent to an infinite number of conserved forms like this. So if I pick any n, it's not 0 or -1, then this equation here is equivalent to this equation here. And when the solutions are continuous, when the data is continuous, the solutions will be identical. When you have shock solutions, the shock speed explicitly depends on n, as we see on the movies on the right-hand side. So finding the correct conservation law form is one of the ways of guaranteeing that you get a unique solution. If you don't have the correct conservation law form and you just use any old numerical method, then essentially the value of n, and hence the shock speed that you have here, will be set by the numerical method, not by the physics. Now, there are alternatives. You can use entropy pairs, there's path-consistent methods, but if you have a conservation law form, then you should always be using it. Now, I have a mention here of the summation by parts form that now appears to be defunct. I think the summation by parts approaches are now built into things like Crank and NumPy that generate the schemes. Just briefly on entropy functions, when I talk about entropy functions, what I mean is a convex function of the state vector that is consistent with the equations of motion. For example, consistent with the balance law in this form. What this does is it guarantees that the entropy is non-increasing. Now, you might think that's the wrong way round. That's because this is a mathematical entropy, not a physical entropy. So for hydrodynamics, the mathematical entropy is essentially minus the physical entropy. You can also think of this as an energy. If your numerical method is obeying this entropy inequality, then you will pick up an appropriate solution. If, on the other hand, you have two solutions and one of them is not an entropy solution, then no matter how close those two solutions start, it is possible for them to diverge exponentially in time. So using entropy solutions allows us to pick out the appropriate one of these different forms, even when they start arbitrarily close together. The conclusion from this is that if your numerical scheme violates the entropy condition, then there will be initial data that can diverge exponentially quickly from the true solution. Okay, so moving on to our final type of numerical method, which is the spectral elements. That's finite elements where within a given cell, we are representing the data using multiple pieces of information so that it looks like a function basis expansion. Once again, we use the weak form. We essentially integrate over the cell after multiplying by some smooth function. And what this does is it replaces our PDE, for example, a balance law, with a dense mass matrix multiplied by the time derivative of the modal coefficients plus the stiffness matrix multiplied by something that represents how the derivatives of the modal solution behave inside one given cell. So this is purely local. It just uses information within the cell. And then finally, we have, well, we've done a weak solution, so we're integrating over the cell. So this term here comes from the boundary terms, the communication between neighboring cells. Okay? So the advantage of this method, the key advantage, is that we do not have a large stencil. All of this here uses information purely available inside a single computational cell. Only the term on the right-hand side communicates with neighboring cells, and therefore only this needs to consider stuff that might be living on another processor. So the huge advantage of spectral element methods is that they are very local while still managing to give us high order accuracy. As we increase the number of modes, we expect to get spectral accuracy with the modes. Okay, so if there's a discontinuity inside the particular element, we would expect Gibbs effects. But we can get around this by essentially keeping elements near shocks relatively small, or doing some sort of limiting inside an element, or so on and so forth. Okay, so these methods are expensive and complex, partially because these matrices M and S are dense and the size scales with the number of modes and also the number of dimensions. So if you're working on a single processor, working with simple, smooth problems, then actually the advantage of these methods is not so huge. This runtime versus error plot here has DG methods using dashed lines, and we know methods using solid lines. And we can see for comparable convergence rates, so that would be the blue and yellow line here, or the red and blue line here, there's actually little to choose between the DG and the we know methods. This is where using cell counts obviously is very misleading, because the cost per cell of DG is so much higher than the cost per cell of we know methods. However, the huge advantage on modern massively parallel GPU machines is the enormous reduction in communication of a spectral element discontinuous Galerkin method compared to a we know scheme that has a very large stencil. Once again, because of the grid and communication model within the Einstein Toolkit, there is no spectral element code for doing evolution. Instead, you're looking at spectra. Okay. Where the toolkit does shine is, of course, in mesh refinement. So this allows us to reduce the grid cells where it is needed in order to improve or decrease the error while minimizing the amount of resource that is used. And of course, yesterday afternoon, there was a detailed introduction to the use of Carpet X and for mesh refinement. Just want to emphasize that the key problems that we have with mesh refinement when it comes to numerical accuracy is through the boundaries of grids. This is where we need to get information onto the fine grid from its parent grid. And we do this via interpolation. So that can have a big source of error, has a large impact on phase error in particular. So there's been lots of work with many different mesh refinement codes in order to try and minimize this. This is particularly the case if you need to do or want to do subcycling in time. That is where the coarser and finer grids use different time steps, which is the way of maximizing the advantages of the efficiency of mesh refinement. So that interpolation in time can be a very nasty source of error, as we found in the original Carpet papers. Now, there is another way that you can use mesh refinement or use multiple overlapping patches in order to improve your efficiency, particularly for wave propagation problems. And that is because physics is not Cartesian. We expect the systems that we're working with to essentially have roughly spherical geometries, particularly at large radius. And this has been implemented in a number of different contexts. So the Llama code within the toolkit uses multiple overlapping patches together with mesh refinement in order to give patches that will follow the merging objects while still giving a roughly spherical grid that captures the wave zone with minimum resources at larger radius. Now, Llama is a very, very complex code to use, and I am not sure if it works. In fact, I'm almost certain it does not work with Carpet. The chances of it actually working are going to be slim, but if you have the problem that really needs high accuracy, then it is a potential way to work. It's also worth looking at Zach Etienne's BH at home code that follows on from NumPy, because that's another way of constructing complex gridding structures to optimize efficiency, but that is not within the toolkit. Okay, so I will just rapidly summarize. So I want to emphasize that the toolkit is optimized for block structured mesh refinement on CPUs using relatively simple methods. CarpetX is busy adding GPU support, but we're always going to be limited by the design decisions that we have made early on. The fact that it still manages to work and work to good enough efficiency for a current production is not guaranteed to hold for the long term, but is definitely working for current problems. The challenges that I particularly would think of would be the accuracy requirements that we're looking at in sort of 10, 15 years' time. For that, we need better numerical methods. We need more resources as ever. The ability to deal with physics that relies on small time steps, so that's stiff source terms, particularly when it comes to reaction networks and neutrinos, and the ability to do efficient parameter surveys and uncertainty quantifications. I touch on a few potential directions that may be worth looking at. So well-balanced schemes are where your simulation is very close to something that is static in a particular coordinate system. So there's ways of hugely increasing accuracy there. There's a few people that are currently looking at that, not currently within the toolkit, but as something maybe worth expanding on. There's the rather unfortunately named alternative finite difference Wino schemes, which are a different way of including Riemann solvers within efficient finite difference methods. They may be much more practical for dealing with more complex physics where we don't have a nice balanced law form because they extend nicely to that. And finally, the use of adaptive modeling, where rather than solving the full nonlinear problem in all its gory glory, we instead replace certain aspects with approximations in order to make the most of efficient numerical methods wherever possible. And with that, I will stop. Thank you very much for your attention, and I'll take some questions.
Thank you very much, Ian, for this very nice lecture. So